It is dangerously easy right now to mistake a prototype for a product.
Oh, absolutely. It happens all the time.
Right. I mean, you spin up a Jupyter notebook, you pull down an API key, write a clever system prompt.
And you feel like a genius.
Exactly. Within an afternoon, you have this AI that writes functional Python code or, analyzes a massive financial spreadsheet. It feels incredibly powerful.
It does. But taking that fragile single-user demo and deploying it into a rigorous, highly concurrent enterprise environment.
Yet where you have actual service level agreements to meet.
Right. SLAs, strict VPC security requirements, and, well, a CFO who is heavily scrutinizing your cloud compute bill. That is a completely different universe.
It really is. Suddenly, you aren't just sending text to an endpoint anymore. You're engineering a distributed system.
And that is the exact inflection point where so many development teams just hit a wall.
Yeah.
When you move to production, that illusion of this omnipotent, monolithic AI brain just completely shatters.
What are you actually left with then?
You're left with an unforgiving landscape of distributed systems architecture. It's an environment where you are forced to make ruthless mathematical trade-offs at every single layer of the stack.
And navigating that exact landscape is why we are here today. For this deep dive, we are dissecting a highly strategic, intensely technical stack of source material.
It's a great blueprint.
Yeah, it's titled Architecting Production Gen AI on AWS, a blueprint for customization, evaluation, and optimization. And just to be clear with you listening right now, we are assuming you already know your way around the AWS ecosystem and the fundamentals of machine learning.
Right, we're not going to spend time defining what a transformer model is.
Exactly. Or, explaining the basics of tokenization. Our mission today is to decode the specific architectural mechanics of this blueprint.
Getting into the real nuts and bolts.
We're going to explore how you technically execute customization at scale, how you programmatically evaluate output when human review is just totally impossible.
Yeah, you can't have humans reading millions of logs.
Exactly. And finally, how you optimize the routing logic so your infrastructure costs don't just spiral completely out of control.
Which is an existential threat to a lot of Gen AI projects right now, to be honest. If you don't build the architecture with those constraints in mind from day one,
You're in trouble.
You will engineer a system that might be brilliant, sure, but it's fundamentally too expensive to actually operate.
Okay, let's unpack this. The source material immediately forces us to confront this reality by establishing what it calls the governing law of generative AI.
Yes, the iron triangle.
Right. It frames this as a trilemma consisting of cost, quality, and latency.
It's the foundational physics of the environment. I mean, before you even look at foundation models, before you start designing your vector databases, you have to map your specific business use case against this trilemma.
And the blueprint defines these three axes very, very specifically for the Gen AI context. Like, cost isn't just your monthly API burn rate.
Oh, no, not at all.
It encompasses the total computational and financial overhead. So we're talking about the vast compute required for training or fine-tuning, the persistent infrastructure costs of, hosting a model in a secure enclave.
Which gets very pricey.
And the variable per token pricing during inference.
Right. And then you have quality.
Which is defined strictly here as accuracy, factual consistency, contextual relevance, and adherence to safety guardrails. It's not just generating fluent English.
No, any model can generate fluent English now. Quality is about being correct. And then latency is the strict time to first token and your overall system throughput.
So how do these three interact?
Well, here is the key insight the blueprint explicitly warns builders about. If you are optimizing for a real-time application, meaning you have a fixed latency constraint because, say, a human user or a downstream system is literally waiting for the response, improving quality will exponentially increase your cost.
Okay, now I have to push back on the physics of that specific word, exponentially. Because, in traditional software engineering or web hosting, scaling is usually relatively linear.
Sure, yeah.
Like it's that old project management, triangle fast, cheap, good, pick two. If I need to handle twice the web traffic at the same speed, I horizontally scale. I provision twice the instances. My cost doubles. It's linear. Why does this blueprint insist that pushing for higher quality in Gen AI results in an exponential explosion in cost?
That's a great question. It's because we are dealing with the inherent bottlenecks of tensor operations and memory bandwidth, not just handling standard HTTP requests.
Okay, walk me through that.
So imagine you have a strict 2-second latency SLA, and you decide your current, say, 8 billion parameter model just isn't giving you the reasoning quality you need.
Right, it's making logical mistakes.
Exactly. You can't just run that same small model for longer to make it smarter. It doesn't work that way. You have to upgrade to a much larger model, maybe a 70 billion parameter model.
Right, increasing the parameter count to increase the capacity for reasoning and factual recall.
Exactly. But a 70 billion parameter model doesn't just require more disk space. The active memory footprint during inference is massive.
Oh, so it's a hardware limitation.
Huge limitation. To run inference on a model that size fast enough to actually hit your 2-second latency limit, you can't just use a slightly better processor.
What do you have to do?
You are forced to distribute that model across multiple high-end accelerators, like an 8-way GPU node. And you're relying on ultra-fast interconnects just to share the weights across the processors in real time.
Wow.
The capital expenditure for that hardware, or, the hourly rate to lease it with provision throughput on AWS, it scales wildly out of proportion to the incremental gain in quality.
So I might pay 10 times the price for a small boost.
Exactly. You might get a 15% bump in your accuracy metrics, but your infrastructure costs just jumped by 10x.
And that completely limits your ability to serve high volumes of concurrent users. It's a harsh reality check.
It really is.
You cannot cheat the trilemma. You simply cannot engineer a system that delivers maximum reasoning quality, instantaneous response times, and minimal compute costs.
And if we connect this to the bigger picture, this trilemma is the forcing function for every single architectural decision we are going to discuss today.
Because you can't just throw money at a bigger model.
Right. You have to build systems that manipulate these three levers dynamically.
Which transitions us perfectly into the mechanics of how we actually control model behavior. I mean, if we are constrained by this trilemma, we need specific tools to adjust these levers. We need highly optimized methods to customize the AI without destroying our latency or our budget.
Exactly.
And the blueprint maps this out on what it calls the quality customization spectrum.
Right. This spectrum is essentially the control panel for an AI architect.
It outlines 4 distinct techniques, right?
Yeah, 4 main methods for injecting custom knowledge or behavior into a foundation model. And it scales all the way from entirely stateless interactions up to fundamentally altering the model's neural weights.
Okay, let's analyze the endpoints of this spectrum first. On the lightest end, we have in-context learning, or ICL.
The easiest one.
Right. The blueprint shows the resource cost and data preparation requirements here as basically 0, but it has very low task specificity. This is entirely stateless.
Yes. You aren't changing the model at all. You are just utilizing its existing pre-trained weights and leveraging its attention mechanism. You're just passing instructions and examples directly inside the runtime prompt.
So what's the catch?
Well, it's highly flexible, but as you scale, in-context learning hits a hard ceiling. You are entirely bound by the context window limit.
And those windows are getting bigger, right?
They are, but even if a model boasts a 200,000 token context window, packing that window full of examples for every single API call massively degrades your latency, and it spikes your per transaction cost.
Right, because the attention mechanism scales quadratically.
Exactly.
The model literally has to compute the relationship between every single token you just shoved into the prompt before it can generate a single word of output.
Precisely. So when ICL fails to scale, architects look to the heaviest end of the spectrum, continuous pre-training, or what some people call domain adaptation.
I was looking at the compute requirements for continuous pre-training in the blueprint, and honestly, it looks nearly indistinguishable from training a foundation model from scratch.
It basically is.
The sliders for resource cost and data requirements are just maxed out. You need massive clusters, and importantly, the data required is vast amounts of unstructured, unlabeled domain data. You're essentially forcing the model to absorb an entirely new foundation of reality.
Yes, think about a highly specialized domain like proprietary genomics research or internal mainframe code languages developed in the 1980s.
Stuff it would never find on the public internet.
Exactly. A standard foundation model simply lacks the statistical vocabulary to reason about that data. By running continuous pre-training over terabytes of your internal data, you are updating the model's base weights so it fundamentally understands the semantic relationships of your specific industry jargon.
But
The cost is astronomical. It requires millions of GPU hours.
So it's basically rebuilding the foundational schema of the model's worldview. That is not something a mid-sized enterprise does casually.
Oh, never.
Which brings us to the middle of the spectrum, the techniques that actually allow us to scale production AI efficiently. We have retrieval augmented generation, or free, and fine-tuning. And here's where it gets really interesting because the blueprint draws a very hard line between these two. It contrasts task specialization versus domain absorption.
And this is a critical distinction that often gets muddled by developers. Engineers frequently try to use fine-tuning to teach a model new facts, which is a massive anti-pattern.
The blueprint is very explicit about this. Fine-tuning is for task specialization.
Right.
The objective is to alter the model's behavior, its tone, or its output structure. You use limited, highly structured, labeled datasets. For example, if you need the model to consistently output complex nested JSON payloads that match a very strict internal schema, you fine-tune it.
Yes.
You do not fine-tune it to memorize your updated product catalog.
Because neural network weights are not a relational database. They are statistical probabilities. If you try to bake your product catalog into the model's weights via fine-tuning, the model will inevitably hallucinate product numbers or mix up pricing.
But historically, even behavioral fine-tuning was incredibly expensive, right?
Mhm.
Because you were updating billions of parameters.
It was. But the blueprint highlights a specific architectural breakthrough that has completely changed the economics of enterprise AI.
Parameter-efficient fine-tuning.
Exactly. Specifically, low-rank adaptation, or LoRA.
What's fascinating here is the elegant mathematics behind LoRA. I mean, it basically solved one of the biggest financial bottlenecks in machine learning.
It really did.
Let's dive into the mechanics of this because the blueprint includes a great visualization of how LoRA impacts the compute environment.
I love this diagram.
Yeah, it shows a massive block representing the frozen foundation model weights. And during the fine-tuning process, the data does not update this massive block. Instead, there is a much smaller module, the LoRA adapter, where the actual learning happens.
Right. Instead of updating a massive, say, 10,000 by 10,000 weight matrix, LoRa decomposes that update into two much smaller, low-rank matrices.
And that decomposition is the genius of it.
Mhm.
Like, let's say you want to update the attention weights of a massive model. Normally, during backpropagation, the optimizer has to store the gradient states, the momentum, the variance, for every single one of those billions of parameters.
And that requires an immense amount of VRAM. You often run out of memory before you even start computing.
But with LoRa, you freeze the original weights entirely.
Yes.
You introduce these two smaller matrices, which are often representing just a tiny fraction of a percent of the total parameters. And during the forward pass, the input is processed by the frozen weights and simultaneously processed by your tiny LoRa matrices. And then the results are just added together.
Exactly. Because you are only calculating gradients and updating the weights of those tiny matrices, your optimizer memory footprint shrinks drastically.
It's much cheaper.
Unbelievably cheaper. You can fine-tune a massive foundation model on a single high-end GPU instance in a matter of hours, rather than spinning up a multi-node cluster for days.
It's essentially like deploying a lightweight, transparent computational overlay on top of the foundation model.
That's a perfect analogy.
It's like taking a massive, unchangeable encyclopedia, the frozen model, and simply slipping a specialized, lightweight, transparent overlay on top of the pages to highlight exactly what you need without rewriting the whole book.
I love that. And you can have dozens of these adapters.
Totally.
Oh, yeah. You can
Yeah.
have one for your SQL generation, one for your customer support tone, and you just swap them in and out at runtime over the same frozen base model.
That modularity is what makes it so powerful for enterprise environments.
Mhm.
But as the blueprint details the IDE parameter inspector section, training that overlay still requires precise engineering. It isn't just plug and play.
Oh, not at all.
The blueprint exposes 4 critical hyperparameters for fine-tuning that architects have to tightly manage. Let's break down the mechanics of these. First, we have epochs, which is generally set between 1 and 10. Now, we know an epoch is a full pass through the training data set, but what is the actual architectural risk here?
The primary risk is overfitting.
Okay.
Your goal with task specialization isn't rote memorization, it's pattern generalization. If you set your epochs too high, the model's weights become hyper-optimized to your exact training examples.
And why is that bad?
Because when it encounters a slight variation in production, it fails completely. The localized loss minimum it found during training is just too steep. Keeping epochs low ensures the model learns the structural pattern without losing the flexible reasoning capabilities of the frozen base model.
Makes sense. Then we have batch size, which is the number of examples processed before updating the gradients.
Right, and this is a pure hardware trade-off.
Yeah.
A larger batch size gives you a much more stable, accurate gradient update because it's averaging the loss over more examples. It smooths out the learning curve, But holding all those activations in memory requires massive VRAM.
So if you're on a budget.
If you don't have the hardware, you are forced to use a smaller batch size and rely on gradient accumulation techniques, which just increases your overall training time.
Got it. The third hyperparameter is learning rate. And the values listed here are incredibly small, like 0.00001 to 0.0000001. That controls the step size of the weight adjustments during gradient descent. Why so tiny?
This is arguably the most sensitive dial on the whole board. The loss landscape of a foundation model is incredibly complex. If your learning rate is too large, your updates will violently overshoot the optimal minima, and the model's output will degrade into absolute garbage.
Like it just spits out nonsense.
You will literally destroy its ability to generate coherent text. So those tiny fractional numbers represent a highly conservative approach to nudging the behavior without destabilizing the pre-trained representations.
And to further protect against that destabilization, the blueprint lists warm-up steps, usually up to 250.
Right, because when training initiates, the random initialization of the LoRa matrices means your initial gradients are going to be chaotic. They'll be highly inaccurate.
Oh, so you don't want to learn too fast from bad initial guesses.
Exactly. If you apply your full learning rate to those chaotic gradients, you severely disrupt the training trajectory. Warm-up steps act as a governor. You start the learning rate at near zero and linearly scale it up over the first few hundred steps. It allows the matrices to stabilize before making any significant updates.
So what does this all mean? It means that through careful hyperparameter tuning and LoRa architecture, we can lock in specific model behaviors efficiently. But that brings up a massive architectural bottleneck.
Yep.
If LoRa is strictly for behavior, and we explicitly shouldn't use it to teach the model new facts, how do we safely integrate our massive, constantly changing proprietary databases?
And that forces us to look at the other pillar of the customization spectrum.
Retrieval augmented generation, RH.
Exactly. This is where we shift from managing internal model weights to managing external state.
The blueprint lays out a very clear decision framework in a section titled The Final Router, RAG versus Customization. It dictates that you must use RAG if you require real-time data, need flexibility across multiple domains, and are optimizing to reduce retraining cycles.
Which is most enterprise use cases, frankly.
Right, and conversely, you use customization like LoRa if your data is static, you need high accuracy on specific execution formats, and you actually have the MLOps pipeline to handle versioning and retraining.
It creates a very clean separation of concerns. RAG is your dynamic knowledge retrieval engine. Customization is your behavioral execution engine.
But, and this is a big but, the blueprint dives deeply into the pricing mechanics of production AI to issue a major warning about RAG. There's this persistent myth that because RAG avoids the compute costs of fine-tuning, it is inherently cheap.
Oh, it is not cheap.
The math provided here paints a very different picture. The total transaction cost is the base API cost formula plus the RAG retrieval token cost.
And this is exactly where the context window trap catches so many development teams off guard.
Let's look at the base API formula. Input tokens divided by 1,000 multiplied by the input rate, plus output tokens divided by 1,000 multiplied by the output rate. Now, we know output tokens are computationally heavier to generate, so they cost more.
Right.
But the real issue is the input side. The blueprint highlights a key insight. Context windows are not free. Injecting 100 pages of RAG context into every single prompt shifts the cost bottleneck completely from generation to retrieval.
We touched on this earlier with the quadratic scaling of the attention mechanism, but let's apply it directly to RAG economics. Let's say a user asks a simple, 20 token question.
Super short.
In a naive RAG setup, your vector database retrieves the top 20 most relevant internal documents. That could be 50,000 tokens of text. And it silently injects all of it into the system prompt.
Oh, wow.
So the model now has to process 50,020 input tokens for a single, simple query.
So your per transaction cost just exploded.
Completely exploded, and your latency just tanked. Because the time to first token is bound by the model's need to compute the self-attention over those 50,000 tokens.
So what's the solution?
The architectural mandate here isn't to retrieve as much context as possible. It is to engineer highly precise vector search algorithms using techniques like hybrid keyword and dense vector search or cross-encoder re-ranking to retrieve the absolute minimum amount of context required to ground the answer.
You want to send the model a single highly relevant paragraph. You do not want to send the entire manual.
Exactly.
And we haven't even talked about the knowledge-based building cost detailed in the blueprint. To even enable AG, you have to convert your raw data into embeddings. The formula is total tokens multiplied by the embedding model input cost.
And embedding 10 gigabytes of text isn't trivial. It requires running all that text through a dense embedding model to map the semantic meaning into high-dimensional vector space. And then you have to index those vectors, often using complex algorithms like hierarchical navigable small world graphs or HNSW, just so they can be searched in milliseconds. That indexing process is highly compute intensive.
Okay, so let's summarize where we are. We have all these isolated components. We have our vector databases for dynamic knowledge.
Sure.
We have our LoRa adapters for structural behavior.
Yeah.
And we are tightly managing our token context to balance the cost-latency trilemma.
Yep, the pieces are on the board.
Now we have to wire them together. How do we orchestrate a system that actually utilizes these tools to perform complex work? This brings us to a highly debated section of the blueprint, wiring the brain. Structured workflows versus autonomous agents.
And this section represents a major reality check for the industry.
Tell me about it.
There is a massive push in the research community right now toward autonomous agents, systems where you give the LLM a goal, give it access to a suite of tools, and just let it determine its own execution path using frameworks like React.
Which stands for reasoning and acting,
Yeah.
right? The blueprint shows a diagram of agentic solutions. And honestly, it looks chaotic. You've got nodes connected with multi-directional arrows representing dynamic decision loops. And the traits listed are high flexibility, but high latency, unpredictable cost, and lower reliability.
Let me explain why React loops and autonomous agents are a nightmare in enterprise production.
Okay.
Say you deploy an agent to resolve customer billing errors. It encounters an edge case. The agent reasons it needs to query the database. The query fails. It reasons it needs to rewrite the query. That fails too. It decides to search the web documentation. It essentially gets stuck in a non-deterministic loop.
Meanwhile, the user's just sitting there waiting.
Exactly. Your API gateway might have a hard time out of 30 seconds. The agent is just happily iterating, burning through expensive output tokens as it generates internal thoughts, and then boom, the connection just drops.
Ouch.
You have unbounded latency, completely unpredictable token costs, and a massive hit to reliability.
Wait, but isn't hard-coding structured workflows just a stopgap? I mean, everyone from the major cloud providers to open-source communities is pushing agentic architectures. If I build a strict, hard-routed workflow today, won't my entire AWS architecture be obsolete in 6 to 12 months when agents become more reliable?
That is a very common concern, but it misunderstands the fundamental nature of enterprise SLAs.
How so?
Even if an agent becomes highly capable, a non-deterministic execution path inherently cannot guarantee a bounded latency limit or a bounded cost per transaction. In an enterprise environment, predictability is often way more valuable than raw flexibility.
That makes a lot of sense.
You need to know that a specific query will resolve in under 2 seconds and cost less than half a cent every single time. Agents cannot guarantee that. Workflows can.
Which is why the blueprint offers this incredibly blunt golden rule. Do not deploy an autonomous agent to perform a job. A strict routing workflow can execute flawlessly at half the latency.
It's about using the right level of cognitive overhead for the task.
So let's break down the 3 specific types of workflow circuitry. The blueprint details to manage this cognitive overhead. Circuit 1 is chaining or sequential execution. The architecture here is straightforward. Prompt enters node A, output of node A goes to node B, output of B to node C.
It's very linear.
The blueprint uses the example of decomposing complex tasks, like having one model generate an outline, passing that to a second model to draft the content, and a third to translate it.
Chaining manages state and attention focus. If you ask a single model to outline, draft, and translate a 10,000-word document all in one pass, its attention mechanism gets diluted across multiple distinct objectives.
It'll lose track of what it's doing.
It will inevitably drift or hallucinate. But by isolating each step into a sequential chain, each node has a highly focused, localized prompt. The quality of the final output is drastically higher.
But the trade-off, because we are always bound by the trilemma, is latency. You are paying the time to first token penalty 3 separate times.
Correct. You are explicitly trading latency for quality.
Which leads us to Circuit 2, the routing or dynamic circuitry. And this feels like the holy grail of cost optimization. The diagram shows a prompt hitting a router switch.
Yeah.
Based on the input complexity, it routes the prompt down to a fast cheat model or up to a slow smart model. How does this router switch technically execute this without adding massive latency itself?
This is usually implemented as a semantic router. It doesn't use a massive generative model to make the decision.
Oh, it doesn't.
No, that would be too slow. Instead, it uses a very small, incredibly fast embedding model or a lightweight classifier. As the prompt comes in, it maps the intent against a predefined threshold.
Can you give an example?
Sure, if the user asks, how do I reset my password? The semantic router instantly matches that to a low complexity cluster and routes the payload to an inexpensive 8 billion parameter model.
And the user gets an answer in milliseconds, and it costs you fractions of a penny.
Exactly. But if the user submits a massive payload detailing a complex API integration failure, the router detects the high semantic complexity, and it dynamically routes the request to your massive, computationally expensive flagship model.
So by dynamically tiering the compute, you reserve your expensive infrastructure strictly for the edge cases that actually require it. That vastly lowers your aggregate transaction costs across millions of users.
It is the ultimate architectural hack for the trilemma.
So what does this all mean for the final workflow? Circuit 3 is parallelization for throughput. A prompt hits a splitter node, fans out to model A, B, and C simultaneously, and then an aggregator node synthesizes the parallel outputs.
This is a classic MapReduce pattern adapted for GenAI.
Right.
If a financial analyst needs to summarize earnings reports across 5 different companies, you don't process them sequentially. You fan out 5 concurrent Lambda invocations, process the summaries in parallel, and then fan into an aggregator model that formats the final report.
So you drastically reduce the overall wall clock latency compared to a sequential chain.
Exactly.
Okay, so we've engineered this highly efficient, heavily optimized assembly line. But this introduces a massive vulnerability. We have all these nodes generating outputs and passing them downstream. If node A in a chain sneaks a subtle hallucination into the context, node B is going to blindly expand on that hallucination.
It compounds.
Right. By the time it hits the user, the errors is completely baked in. How on earth do we catch these failures at scale when human review is impossible?
This is where architecture meets MLOps. Evaluation cannot be an afterthought. It must be an automated, integrated layer of the pipeline.
The blueprint dedicates Section 6 to the evaluation engine grading the AI. It immediately establishes that relying on human grading for production telemetry is a non-starter. You have to rely on automated diagnostics to filter baseline performance.
You need a dashboard.
The dashboard lists a series of deterministic metrics. Accuracy and classification accuracy are standard for structured outputs, but then we get to BERT score. The blueprint defines this as evaluating semantic similarity between generated and reference text. How does this differ from traditional keyword matching?
Well, in traditional natural language processing, metrics like BLU or Rouge relied heavily on lexical overlap,
Meaning?
counting how many exact words match between the model's output and a golden reference answer. But GenAI models are highly paraphrastic.
They use different words to say the same thing.
Right. If the reference answer is the connection timed out, and the model outputs the network request exceeded the timeout threshold, a lexical metric might score that very low, even though the factual meaning is perfect.
Because the exact strings don't match.
Exactly. BERT score solves this by comparing the deep contextual embeddings of the words. It uses a bidirectional encoder to map both sentences into vector space and calculates the cosine similarity between them.
Oh.
It mathematically proves that the semantic meaning is identical, allowing you to automatically grade the accuracy of free-form text generation.
That is critical for automated telemetry. The dashboard also tracks robustness, visualizing resistance to input perturbations. If a user injects typos, weird formatting, or adversarial noise into the prompt, does the model's logic collapse?
And you have to track toxicity, which is non-negotiable for enterprise brand safety.
Right. You have to run fast classification models on the output to detect harmful language before it ever hits the user interface.
But these deterministic metrics, even BERT score, fall short when you are trying to evaluate highly complex subjective qualities. You can't use a mathematical formula to determine if an executive summary is persuasive or if a generated email strikes the right empathetic tone.
Which introduces the most controversial architecture in the blueprint, scaling nuance, LLM as a judge.
This is a hot topic.
The diagram shows outputs from 2 peer models, Model X and Model Y, being fed into a dedicated LLM judge node powered by a superior foundation model like Claude 3 Opus. The judge evaluates the outputs against a strict scoring rubric and spits out a definitive qualitative score. Now, I have to challenge this concept fundamentally.
Go for it.
Isn't it inherently dangerous and mathematically circular to rely on an AI to grade the logic and accuracy of another AI? We know these models suffer from sycophancy. They have positional biases depending on which answer is presented first, and they hallucinate. Who is grading the judge?
This is the subject of intense debate among AI safety researchers. It
Yeah.
feels circular, but again, we have to look at the practical reality of production architecture.
Okay, what's the reality?
If you are serving 100,000 queries a day and you deploy a new LoRa adapter, you need to know quantitatively if the tone improved or degraded across those 100,000 interactions. You cannot hire an army of human annotators to read them. LLM as a judge is quite literally the only mechanism that scales.
So we just accept the risk and trust the bigger model.
No, we engineer around the risk. What's fascinating here is how you constrain the judge. You don't just pass the text and ask, is this good?
What do you do instead?
You deploy massive, highly structured system prompts, often utilizing a technique called few-shot prompting with chain-of-thought reasoning. You provide the judge with an exhaustive mathematical rubric. You explicitly define what clarity means on a 1 to 5 scale. You provide examples of a score of 2 versus a score of 4.
Oh, so you're really boxing it in.
Yes, you force the judge to output its reasoning step by step before it outputs the final score, which drastically reduces hallucination.
You are essentially trying to strip away the model's creative freedom and force it to act as a deterministic grading algorithm.
Precisely. You calculate metrics like Cohen's kappa on a small sample to ensure the LMR's judge highly correlates with human expert graders. Once that correlation is verified, you let the judge run autonomously at scale.
That makes sense for generative tasks. What happens when we apply evaluation to our RAG pipelines? Earlier, we established how critical vector search is, but the blueprint explicitly warns. Knowledge-based evaluation architecture requires isolating retrieval hallucination from generation hallucination. It states that RAG systems fail in two distinct, deeply separate ways.
And this is a classic diagnostic trap that wastes countless engineering hours.
How so?
A user asks a question, and the RAG system outputs a completely incorrect, hallucinated answer. The knee-jerk reaction from the development team is, the generative model is broken, the reasoning is flawed, we need to upgrade to a more expensive model.
But the blueprint forces you to evaluate the pipeline in two distinct stages. Stage 1 is retrieval quality. The metrics here are relevance and correctness, often measured using search metrics like mean reciprocal rank or normalized discounted cumulative gain.
Right.
Did our vector database actually fetch the right documents containing the factual answer?
If a user asks for the Q3 revenue numbers, and your dense embedding search retrieves the Q2 marketing strategy document, the generative model is guaranteed to fail.
Because it doesn't have the right information.
Exactly. The model isn't broken, the context it was fed is useless. That is a stage 1 failure. You fix that by tuning your chunking strategy, upgrading your embedding model, or implementing a cross-encoder re-ranker. You do not touch the generative model.
Okay, but let's assume stage 1 is perfect. The vector search retrieves the exact paragraph containing the Q3 revenue. That context is injected into the prompt and passed to the LLM. This is stage 2, response quality. The metrics here are faithfulness and logical coherence. The core evaluation question is the generated answer grounded strictly in the retrieved context?
And this is where you use LLM as a judge to detect generation hallucinations. You feed the judge the user prompt, the retrieved context, and the model's final answer. The judge's only job is to verify if every single factual claim made in the final answer is explicitly supported by the context paragraph.
So if the context says revenue was $5 million, and the model confidently states revenue was $50 million.
That is a stage 2 failure. The model ignored the context.
By decoupling the evaluation into retrieval quality versus response quality, architects can pinpoint the exact node in the system that is failing and apply the correct engineering fix rather than just blindly swapping out models.
It brings deterministic software engineering practices to probabilistic AI systems.
Incredible. We have systematically unpacked every isolated layer of this blueprint. We understand the unyielding physics of the cost-quality latency trilemma. We've explored the deep parameter mechanics of LoRa customization and the token economics of vector-based R.
We've covered a lot of ground.
We really have. We've debated the necessity of hard-coded routing workflows over autonomous agents, and we've architected an automated LLM-driven evaluation pipeline to catch hallucinations at scale. It is finally time to zoom out.
The big picture.
The final diagram in our source material synthesizes all of this into one massive overarching architecture titled the Grand Architecture, the Production Generative AI Lifecycle.
This is the 10,000-foot view. This is what a mature, highly concurrent, enterprise-grade AI deployment actually looks like running inside an AWS environment.
Let's trace the life cycle of a single, complex user request as it traverses this machine. Step 1. The user prompt enters the system via the API gateway.
Immediately, it hits our Circuit 2 mechanism, the decision router. A sub-millisecond semantic classifier analyzes the intent and complexity of the prompt to determine the most cost-effective execution path.
Step 2. The workflow diverges. Let's say the prompt requires highly specific formatted reasoning but no external facts. The router sends it down the customization path, invoking a massive frozen foundation model equipped with our hyperspecific LoRa adapter.
Ensuring the output behavior is perfect without burning excess compute.
Right. Or, if the prompt asks a question about a live internal database, the router sends it up the Arrowgate pipeline. The prompt is embedded, the vector database executes a sub-second to nearest neighbor search, retrieves the precise context chunk, and passes it to the generation node.
Step 3. Both of those paths, whether customized behavior or augmented generation, converge. The raw output is immediately intercepted by the automated evaluation node.
This is the deterministic safety checkpoint. It runs the toxicity classifiers and robustness checks. If the output violates brand safety, the transaction is killed instantly.
If it passes the automated checks, we move to step 4, scalable nuance. The output flows into the LLM as a judge node. Our superior evaluator model checks the response against the strict scoring rubric for faithfulness to the context and overall clarity, and it logs all that telemetry data for the MLOps team.
Step 5. If this is a parallelized request, say searching 3 databases simultaneously, it hits the final aggregator node to be synthesized into a single, coherent response.
And finally, step 6, user delivery. The sanitized, evaluated, properly formatted response is delivered back to the client application, all within the strict latency boundaries we established on day 1.
Looking at this entire flow, tracking the request as it bounces between routers, vector databases, LoRa adapters, and evaluator models, it completely shatters the illusion of the single AI brain.
It really does.
Production Gen AI is deeply structured, meticulously monitored, distributed systems engineering. It is a machine made of smaller, highly specialized machines.
And the blueprint leaves us with a core mantra at the very bottom of this final diagram. It is the operating philosophy for everything we've discussed today. Balance the trilemma, measure everything, build with intent.
Balance the trilemma. Measure everything, build with intent. It's the perfect synthesis of the engineering mindset required for this field. If you don't build with deliberate architectural intent, the complexities of scale will overwhelm your system.
It separates the fragile prototypes from the resilient, mission-critical business applications.
It absolutely does.
Yeah.
Now, as we wrap up this deep dive, I want to leave you, the listener, with a final provocative thought to ponder on your own. It builds on our discussion about the evaluation engine.
Oh, this is a good one.
As we increasingly rely on LLMs as a judge to evaluate the quality, coherence, and clarity of our systems at scale, standardizing our massive enterprise architectures against the rubrics defined by a handful of proprietary foundation models, are we slowly letting opaque AI algorithms define what good human communication looks like for the rest of our future?
It's a huge philosophical question.
And perhaps more concerning for an architect, what happens to the integrity of our historical telemetry data, our carefully tuned workflows, and our entire qualitative baseline when the creators of those evaluator models decide to quietly update their internal rubrics overnight?
That is exactly the kind of systemic vulnerability that keeps great architects up at night.
Just remember, the next time you see a seamless, lightning-fast AI response in an enterprise application, it isn't magic. You are looking at the output of a flawlessly executed, highly complex distributed system, aggressively balancing cost and quality in the muddy waters of production. Thank you so much for joining us on this deep dive. We'll catch you on the next one.